Everything that falls into a black hole is gone forever. That's what general relativity says. But quantum mechanics says something else entirely. It says information cannot be destroyed. Not ever. Under any circumstances. The universe keeps a perfect ledger. One of these theories is wrong. This is the black hole information paradox. It has sat at the center of theoretical physics for 50 years. And in 2024, a group of physicists found a new equation, one that might finally tell us where the information goes. The key was measuring entanglement that points backward in time. In 1974, Stephen Hawking proved something that stunned everyone. Black holes are not perfectly black. They evaporate. Slowly, over timescales that dwarf the age of the universe for stellar mass black holes. But they evaporate. As a black hole shrinks, it radiates photons. Hawking showed this using quantum field theory near the event horizon, the boundary of no return. The problem is what that radiation looks like. It's perfectly thermal. Random. Completely featureless. No matter what you throw into a black hole, a rock, a book, a hard drive full of quantum states, the radiation that comes out looks exactly the same. Throw in an encyclopedia. Wait for the black hole to evaporate. You get back random heat. Quantum mechanics says this is impossible. Every quantum process is reversible. Information is conserved. Always. If you throw a quantum state in and get thermal noise out, information was destroyed. This is the black hole information paradox. And for 50 years, no one could resolve it. The resolution comes from entanglement entropy. When Hawking radiation is emitted, each photon leaving the black hole is entangled with the interior. The entanglement entropy of the radiation, how much quantum information it shares with the black hole interior, starts at zero and grows as the black hole evaporates. But here's the question, does it grow forever? Hawking's original calculation says yes. The entropy grows forever, the information is lost, and quantum mechanics is violated. But in 1993, physicist Don Page argued that if quantum mechanics holds, the entropy curve must turn around. The entropy of the radiation should peak around the halfway point of the evaporation, the Page time, and then decrease, tracing back to zero when the black hole is fully gone. This is the Page curve. It's what quantum unitarity demands. For decades, no calculation from quantum gravity could reproduce it. Until 2019, when physicists discovered the island formula, a new way of computing entanglement entropy in gravitational theories. By including a region inside the black hole horizon, an island, in the entropy calculation, the Page curve emerges correctly. The black hole is not destroying information. It's hiding it in quantum correlations. But how exactly? What is the mathematical structure behind this? This is where a 2024 paper by Gua, He, and Zhang changes the picture. Entanglement entropy is normally defined for a region of space at a single moment in time, a space-like interval. 2 points separated by distance. But quantum field theory allows something more exotic. Entanglement entropy defined for 2 points separated in time. This is timelike entanglement entropy. And it's strange. It's complex valued, it has an imaginary part, in addition to a real part. That imaginary part is not an artifact. It's physics. Hua, He, and Zhang derived a precise equation connecting timelike entanglement entropy to spacelike entanglement entropy and its first time derivative on the Cauchy surface. The imaginary part I pi times the central charge over 6 is universal for all states in the vacuum family. Vacuum, thermal, holographic anti de Sitter. Where does it come from? From causality itself. The twist operators used to compute entanglement entropy don't commute with their own time derivatives at the same point. That non-commutativity is the fingerprint of causality embedded in the entanglement structure. The imaginary part of timelike entanglement entropy is the universe's way of encoding that operators at the same point cannot simultaneously have definite values. Now bring this back to black holes. The Ryu-Takayanagi formula, a holographic recipe that connects entanglement entropy to geometry, has two versions. The spacelike version computes entanglement entropy using a minimal spacelike surface in the bulk, the RT surface. For a region outside the black hole, this surface lives in the exterior. The timelike version can involve surfaces that reach inside the horizon. Here is the key insight from Gua, He and Zhang. Their equation establishes a direct mathematical relationship between the timelike Ryu-Takayanagi surface inside the horizon and the spacelike RT surface outside it. In their 2025 follow-up, they proposed this as a duality. Exterior and interior RT surfaces are related exactly by the timelike spacelike entanglement entropy relation. What this means physically, the quantum state inside the black hole is not independent of what's outside. Information about the interior is encoded in the entanglement structure of the exterior radiation. In principle, and this is the profound part, an observer outside the black hole can reconstruct what's inside, without ever crossing the event horizon. This connects to entanglement wedge reconstruction, the idea that the gravitational interior is encoded in the quantum state of the exterior. Their equation gives this a precise, computable form. The Page curve, the island formula, the RT duality, they're all different phases of the same structure. Timelike entanglement entropy is the mathematical thread that ties them together. Three things this changes about how we think about black holes. First, the imaginary part of timelike entanglement entropy, I pi c/6, is a physical observable. A signature of causality in the entanglement structure. It appears in the vacuum, in thermal states, in holographic anti-de Sitter states. It even appears in de Sitter spacetime, the geometry that describes our universe's current expansion. If Hawking radiation carries this structure, it is, in principle, measurable. A fingerprint that causality imprinted on the radiation as it escaped the horizon. Second, timelike and spacelike entanglement entropy are not separate concepts. The equation unifies them in a single framework. What happens along a time interval is constrained by what happens on the Cauchy surface. The universe does not allow timelike entanglement to be independent of spacelike entanglement. This is a new conservation law for quantum information emerging directly from the structure of quantum field theory and causality. Third, and most important, the information paradox may not be a paradox. It is a question about which calculation is correct. Hawking's calculation used semi-classical gravity. No quantum corrections. It gave the wrong entropy curve. The island formula, grounded in the RT duality that this equation formalizes, gives the right curve. The black hole is not destroying information. It is encoding it in timelike quantum correlations, correlations that reach backward and forward in time, across the event horizon, into the radiation carrying the black hole's history outward. The universe keeps its ledger. We're finally learning to read it. Black holes are not the end of information. They are the most extreme quantum information processors the universe has ever built. And the mathematics now exists to start reading what they encode. Next episode, the quantum vacuum. Why empty space isn't empty. How the Casimir effect produces a measurable force from pure vacuum fluctuations. And why the cosmological constant, the energy density of empty space, is off by the largest factor in the history of theoretical physics. 120 orders of magnitude. Subscribe. New physics every week. The stranger it gets, the closer we are to something real. See you next week.